Hello class, I appreciate you watching. In this video, I will go over the review for the third test, which covers section 4.1 through 4.5. Now from 4.1, you're asked to evaluate an exponential expression. So here we have that f of t equals 160 times 2.7 to the 0.07 t power, where t is the time in months. And we want to use this function to determine the population of some forest animal 12 months from that day. So here we're evaluating f of 12, which simply requires us to replace our t, our value of t, with 12. So let's bring out our calculator here. And again, thanks to Numworks for this device here. This is a great little device. And we're going to raise that to the 0.07 times 12 power. And that's going to equal to a total of 369. We'll estimate it to 69. So that's the answer to this question right here. So for the second example, the same thing. The city's growth from 1997 is represented by this function here, where this value is in millions, 5.4 million people. Let me move this out of the way. What is the city's population in the year 2000? So from 1997 to 2000, that means that their time is going to be 7 years. So we're going to evaluate f of 7. And let's see what that's going to approximate to. So 5.416, 2.7. We're going to raise that to the 0.007, multiply that with 7 as well. And that's going to equal to a total of 5.686. And again, And let's move to the right and close that parentheses. And let's put the exponent of 4 times 4. And our estimated value is $641.88. So that's how much the accumulated value of this $400 investment will be if it's compounded quarterly for 4 years at 12%. Okay, moving on to the next part. Let me change the view here to seamless. Okay. For the next page, the back page, is that we want to write these equations in equivalent exponential form. So in this situation, to write it, we start with the base, we raise it to this power, and it equals to the value of the log. So here, 2 to the third power equals to 8, and the one on the right would be 5 to the second power equals to 25. So that's the equivalent exponential form to those two log equations. Now to work backwards, to write the exponential equations into their logarithmic form, we start again with the base, so 5. So we start by writing log base 5 of this value of 1 over 25, and it equals to the exponent, -2. So for the one on the right, this would be log base 3 of 81 equals 4. And that obviously still has to make sense. If I go the other way around, 3 to the power equals 81. So you can check again your work, because if you go backwards and if you're able to do the first two, then that means that your answer here should be giving you this when you write it again into exponential form. Now to identify the domain of log functions, you simply have to get the value of our log, which in this case is going to be x plus 7, and have x plus 7 be greater than 0, and you're going to solve that inequality. So we would subtract 7 from both sides, and x would be less than -7. Greater, this is greater. So our domain as an interval would be an open interval from -7 to + infinity. And we do the same thing on the one on the right. We simply get our, regardless if it's ln, again, ln natural log is still a log. We get the value of our log and have it be greater than 0. So that 7 minus x has to be greater than 0. So here I would add the x to both sides. So add x, that's probably easier to do. And 7 is greater than x. And if 7 is greater than x, that means that x is less than 7. So the values less than 7 are from -infinity to +7 in interval notation. So our domain in interval notation will be written like this. Now, to use the properties of log to expand as much as possible, that's a key thing, that we want to expand as much as possible, and we want to make sure that we evaluate this, okay? So you want to do those two things. If you do not expand as much as possible, then this will end up being incorrect. So the full expanded form of the one on the left here is the common log of 1,000 plus the common log of x. So that's expanded as the problem can get, as this expression can get. However, go back and verify that you have evaluated any log expression when possible. For example, this could be evaluated. The common log of 1,000 equals 4, and we can verify that with our calculator. So if I take the common log, which again is log base 10 of 1,000, that equals 3. So 3 plus the log of x. So there's your answer. And if I'm going to do the one on the right, same thing. If I take the natural log of e to the 7 and add it with the, not added because we're dividing, that means I subtract the natural log of 6. This is again as expanded as I can get. I can do one more thing. I can move this exponent to the front, and using the power property, the fully expanded form of this would be 7 times the natural log of e minus the natural log of 6. So let's see what we end up getting with this situation here. Okay, so let's see. Let's do the natural log of e. Which is just e to the first, okay? So the natural log of e, I forgot to put the 1 right there, is just 1. So this right here equals 1. So we have 7 times, let me put it in parentheses instead of using that notation there, 1. Minus, and let's see what the ln of 6 is. That's some decimal value, which we are not going to use. We're not going to use that 1.79, so we'll just leave it as the natural log of 7. I'm sorry, the natural log of 6. Okay, let me move this back over here. So that means since 7 times 1 is 7, minus ln of 6 is the fully expanded and simplified or expression is evaluated expression as possible. So we end up with that. Now let's say you forgot that we can use this property here where we can pull this to the front, the power property. Well, the good thing that we have our calculator, we can evaluate the log base e of 7, evaluate that, and that's going to give us 7. So this here, I'm sorry, wrong one. This right here in green equals to 7 regardless. So whether you remembered that we can pull the x to the front, the exponent to the front by the power property, and the natural log of e is 1, you can write it as you see right here like I did on my calculator. The natural log of e to the 7th is just 7. So I can do that substitution. And that's going to be the expectation that you write this value or you look for this answer choice, okay? And not anything prior to that, okay? Nothing like this, none of this stuff right there. Okay, not this, not that, or that. Okay, we're looking for that answer choice here. So now let's look at the next examples. Here we want to expand and we have 2 more dividing ones. I'm going to put several of the dividing ones. So the first thing is that we have the log base 3 of x. The square root of x is the same thing as x being raised to the 1/2 power, so you have to make sure that you write it like that, minus the log base 3 of 27. Now here you have to know your power property because this exponent has to be pushed to the front in order to expand this log as much as possible. So the expectation and the correct answer choice will be 1/2 times the log base 3 of x. If you select this answer choice up here with that notation there, that's going to be incorrect. You also have to evaluate this, the log base 3 of 27. Without the calculator, you should be able to calculate 3 to what power gives you 27, and that's going to be to the 3rd power. 3 to the 3rd power is 27, so this is simply 3. But again, since you have your calculator, you can evaluate this using your calculator. So using log base, we can delete this base, replace it with 3. Let's move out of the subscript. Let's move up here. And let's evaluate 27. And that equals 3. So minus 3. So this is your answer. Similarly, for the one on the right, log base 5 of 25 minus the log base 5 of x minus 1 to the 1/2 power. Let's first evaluate the log base 5 of 25. And let's delete the base, and let's change it to 5, and let's put 25 in the parentheses, and that's going to be 2. And that makes perfect sense because 5 to the second power is 25. So this is 2 minus, and here to expand this further, we pull this exponent to the front of our log, and we're going to end up with half log base 5 of x minus 1. So this is the fully expanded log. We expanded the log as much as possible, and we evaluated the first logarithmic expression because we could. We can't evaluate the second one, so we are not going to. Now for the next two equations, you need to solve for the variable x by expressing each side as a power of the same base. And here, well, it's going to kind of be set up for you. The idea is that since on the left side we have an exponential equation with a base 4, that means that this number here somehow can be written as an exponential value of also base 4. So the way we figure that out, if you again do not good with your multiplication, is to simply get 4 and just try numbers. Let's see, let's raise 4 to the 8th power, and that equals to 65,536, so that doesn't work. Let's raise 4, so we want something smaller, to the 6th power, and that equals to 1094, so that doesn't work. So let's raise 4 to something even smaller, let's say to the 4th power, and that's 256, so we want something higher. So 2 to the 5th power, and that equals to 1024. So 4 to the 5th power is equal to this 1024. So that means that 1 plus 2x equals 4 to the 5th. And now because the bases are the same, that means that the exponents are equal to each other. So 1 plus 2x, excuse me, so like I was saying, 1 plus 2x equals 5. So this equation requires us to subtract 1 from both sides, so 2x will equal to 4. Sorry about that. And then we'll divide by 2. So the solution is 2. So x equals 2. So here your answer will be a numerical value. And let's do another similar question. So here the exact same thing. The key thing, again, understanding, because I'm setting up the equation and you have to use again the have each side as a power of the same base. Here the left side is telling you what base that you should use. So 3. So let's see, what power can 3 be raised to in order to get 6561? Let's see, let's try 9. That's way too big. So let's try 8 then. Well, let's try 7. No, that's small, so it has to be 8. So 3 to the 8th power is that. There it is. So that means I can write 361 as 3 to the 8th. So that means here that 5 minus 3x equals 8. So to solve this equation, we'll subtract the 5 from both sides. We'll divide by -3, and x equals -1. And there is your solution. Now for the next exponential equations that have base e for the exponential part, you want to write the solution in terms of the natural log. So as it says, we're going to take the ln to both sides. So here we'll take the ln of e to the x plus 3 equals the ln of 7. And by the power property, I can pull this exponent to the front. So x plus 3 times ln of e equals ln of 7. And just like the prior example, just going back over here, that's why it's important again to know these definitions. As you see right here on this one right here, since the ln of e equals 1, the same thing's going to happen here. This is going to be 1, and 1 times this is going to just give us x plus 3. Well, we could ignore the parentheses. We don't need to write the parentheses. On the right side, we'll just have the ln of 7, and we're going to subtract 3 from both sides. Sorry, that should be a 7. So this is your solution. Similarly, you're going to do have something same happen on the right example. So here we'll take the natural log of e to the 4 minus x equals 5. And again, what essentially happens is that, lack for a better word, is that this cancels out. I forgot to write the ln of 5 because I also have to take the ln of the right side as well. So on the left, we'll just have now 4 minus x equals ln of 5. We'll start by subtracting 4 from both sides. So negative x equals the ln of 5 minus 4. Remember, I cannot combine this. There's technically a parentheses around the 5 that is grouping again with a natural log. Similarly, like the square root. Like the square root of 9 minus 3. I can't subtract the 9 and the 3 and then take the square root. I first have to take the square root and then subtract 3. So kind of the same thing is happening here. Okay, so I cannot subtract these. I have to first take the ln value of 5, and then whatever decimal value I get from there, I can then subtract 4 from that. Now, since our x is negative, I have to divide by negative 1. And dividing by negative 1 makes the 4 positive and makes the ln negative. So my answer would be this, which is the same thing as if you left it as negative ln of 5 plus 4, that would be acceptable as well. I just wrote it backwards since the 4 was positive. But there's your answer. Now let's go back to the previous two problems. So there is another technique using the same technique as I used on these equations right here on solving the exponential equations and writing the answer in terms of log. I can do the same thing here. So this again is just an alternate method. If you for some reason just cannot figure out what power 4 has to be raised to get to 1024, you can just do this. If you take the natural log of the left side, take the natural log of the right side, you can pull this exponent to the front by the power property. And divide both sides by the ln of 4. In this situation, unlike the last two examples that we did, the ln of 4 doesn't reduce. So we'll have to divide by the ln of 4 to reduce these values here. And we end up with 1 plus 2x equals to the natural log of 1024 divided by the natural log of 4. Now this is different than trying to take the natural log of 1024 over 4. That's not the same thing, okay? Here we're going to divide by the natural log of this value and by the natural log of 4. So let's plug that into the calculator. So we'll take our ln of 1024, close the parentheses, and then divide that itself by the ln of 4. And because again the power property works, this is going to then simply equal 5. So this value here is 5. And then we just solve our equation. So we subtract 1 from both sides. So 2x equals 4. We divide by the 2. And x equals 2. The same solution that we got the last time. So this is, again, like I said, it's an alternate form, the alternate technique. If for some reason you cannot just figure out, cannot determine again what the base is, that will give me this to a base of 4. So let's look at the next example. So for this example right here, again, our answer is -1. So let's use the same technique. So instead of, again, figuring out that 3 to the 8th power is equal to 6581, we're just simply going to take the natural log to both sides. So if I take the ln of 3 to the 5 minus 3x and take the ln of 6561, I can pull this exponent by the power property and multiply the ln of 3, the natural log of 3, with 5 minus 3x. That's going to equal to the ln of natural log of 6561. I divide by the natural log of 3. That reduces this side, giving me 5 minus 3x on the left. And let's type this into our calculator and see what we get. So the ln of 6561, divide that by the ln of 3, equals 8. And then we solve the equation. So we'll subtract 3 from both sides, divide by negative 3, and again we get x equals negative 1. So here you have this alternate form. And a couple more equations. The next log equations. Now let's move on to log equations. To solve these log equations, we'll have to use the product property. So on the left side, we have to condense into one log by multiplying x plus 2 with x minus 4, which is going to be x squared minus 2x minus 8. That's again the product of x plus 2 times x minus 4. That equals to 3. What we do now is that we get rid of the log by using our log definition. So basically what we did, let me scroll back up, what we did on the back of the first page, and we're doing this part right here. So if you're able to understand these two examples, well, we're going to use that exact same definition on this example here. So we're going to raise 3 to the third power and equal it to that value there. So I'm going to write x squared minus 2x minus 8, and that's going to equal to 3 to the third power, which is a total of 27. So let me erase this now and bring this over here. Now to solve this equation, because it's a quadratic, because of this term right here, we need this side to be 0. So we're going to subtract 27 from both sides. And now we can break it up into factors. And those factors are going to be negative and positive. And the factors of 35, one factor is 7 times 5. And that works out because 7 and 5 give me a total of negative 2 when I add it together. So x equals to positive 7 or x equals to negative 5. And here, the correct answer is going to be positive 7 only. Because negative 5 will make these logs appear negative. Remember, the domain of a log is whatever makes this greater than 0. So here, x has to be greater than negative 2. X plus 2 greater than 0 means that x has to be greater than negative 2. And since negative 5 is not greater than negative 2, that means that this is out. So x cannot equal to negative 5. And the only solution we have for this equation is x equals 7. So let's look at the next example. Next example, similar situation. We have the log base 2 this time, but we're still going to multiply again x plus 2 and x minus 4. So that's still going to give us x squared minus 2x minus 8, just like on the left problem. So here our x squared minus 2x minus 8 equals 2 this time to the 4th power. So 2 to the 4th power equals 16. So let's erase this and let's bring this over. So this is going to equal to 16. And because of the quadratic, because of this being a quadratic equation, that means that this side has to be 0. So we're going to subtract that 16 from both sides. And now let's factor. And the factors of 24 that give me 2 are going to be 6 and 4. So x equals to 6, or x can equal to -4. And with these log equations, a majority of the time, some of these two solution, when we have quadratics in the logs, we end up seeing that one is an extraneous, and just like the last one, that's going to be the negative number. It just so happens to be the negative number, -4, because again our domain has to be values greater than 4 and greater than -2. And since for this one right here, that one right there, x plus 2 has to be greater than 0, that means that x has to be greater than -2. And -4 is not greater than -2, so -4 is not a solution. And the only solution we have is 6. X equals to 6. Okay. Now let's do two more, but this time when we're subtracting. So we have logs, and there's going to be two things different. The first is that we're not adding, we're subtracting, so that requires us to use the difference property, the quotient property. Subtracting divides those values of log. And the second thing is that we're going to have a log on the left side as well, and also on the right. So we don't have to use the definition, we can use the one-to-one property. So since this common log here equals to this common log there, that means that these values that I'm highlighting in blue also have to equal to each other. So x over x minus 1 equals 42. And to solve this requires just cross multiplication. So x equals 42x minus 42. We'll subtract 42 from both sides. So -41x equals -42. We'll divide both sides by -41. And my answer is going to be this. X equals 42 over 41. Similarly, the same thing's going to happen on the one on the right. I do need to make a correction. I'm just noticing that this should be the log of 12, the common log of 12. So it would be x over x minus 1 equals 12 essentially. Because for the same reasons as what we did over here on the right. I'm just going to not do this step. I'm going to skip this step and go to that step right there, because that's essentially what's going to happen. This log minus this log is going to condense it to one log where x and x minus 1 are being divided. And since it's going to equal to the common log of 12, and again, that was a typo. I did not just add this because I felt it. It's because I meant to have the log of 12. So with the log of 12 here, these are going to equal to each other. So just like before, I'm going to cross multiply, subtract 12 from both sides, divide by -11, and here's your answer. So x equals to 12 over 11. For this problem here, you're just going to simply solve the equation for t. You have that the value of your investments t years after 2000 is given by this function. A equals 4700 times e to the 0.062 t power. And we want to figure out when will the account be worth 8212. So the question is this: what is the value of t that gives us this value? So we're going to replace a, or let me use that notation instead, since we're using a and not a function notation. The question is, what is t equal to when a is 8212? So we're going to replace the a with 8212. So we're going to replace this into this value, and we're going to get that 4700 e to the 0.062t equals to 8212. We'll solve this equation by first dividing both sides by 4700. And let's see, 8212, divide that by 4700. That reduces to 2053 over 1175. I don't want to write the decimal value because again, that's an approximation as you see there. And the fraction notation does reduce. We could divide both sides by, seems like we're dividing by 4. And well, we'll use that number instead, okay? So we have now that e is equal to 0.062. And if you don't want to reduce it, like if you don't want to reduce this fraction and continue using this number, you can, okay? But I'm going to reduce it. I'm going to use that value there. So 2053 over 1175. We now take the natural log to both sides. So the ln to both sides, which in turn, for lack of a better word, cancels out the natural log and the e. So on the left, we only have, there's a t up here, 0.062t equals the natural log of 2053 over 1175. We now divide both sides by 0.062. And there's our answer. So t is going to equal to the natural log of 2053 of over 175, and all of that's divided by 0.062. So that's the exact answer. To figure out the approximated value, well, we now just simply plug that into our calculator. So let's take the natural log of the fraction 2053 divided by 1175. Let's close those parentheses and let's divide that now by 0.062. And that is approximately 9.0005. So let's say that around 9 years, this account that initially started with $4,700 is going to now have $8,212. So the answer would be 9 years. Now for this problem right here, I forgot to write the equation. We want to write the equation in terms of base e and express the answer in terms of a natural log and then round to 3 decimal points. So I was supposed to write this equation 4.75 times 3.4 to the x power. And to rewrite this equation in terms of base e, we start by replacing the 3.4 with e and raising that to the natural log of 3.4 times x. So that's the first part. That's this part right here, expressing the answer in terms of natural log. So that's that part right there. What we have to do now is round to 3 decimal places. So that requires us to evaluate this part right here. So we're going to need our handy dandy calculator here and taking the natural log of only 3.4. That's all I need to do. We're going to write y equals to 4.75 e, and to 3 decimal points, that's 1.224 x. So that would be the second part here. That would be the second part. So there you have it. And finally, for the last 2 questions. For the half-life question, here we have that this silicone 32, the half-life of this thing is 710 years. And we're going to start with 20 grams are present now. So let's use that information here, okay? Now the formula that we use for this half-life, which is the same as the one up here, we just didn't have to figure out what the A sub 0 is A equals to A sub 0, or A initial, e to the kt. It's actually the exact same formula as the continuous compounding. Let me move back up over here to this question right here. So it's the exact same formula that we use for the continuous compounding, with the only difference is that instead of using p for the principal, we use A sub 0 for the initial value, and instead of r for a rate, we use k for a constant of proportionality, okay? A continuous growth, or a constant of the growth, or a constant of decay. So that's the only difference. So you see the formula looks exactly the same. So for this problem right here, if you understand this correctly, you'll understand that this value here equals to 1/2 whenever t is 710 years. So you could automatically set that up. Now, if that doesn't make sense, then think about it like this. Since they're telling us that we're going to start with 20 grams are present right now. Let's plug in 20 here for the initial amount. We can use this information knowing that the half-life is 710 years. That means that when we replace t with 710, this amount is going to decrease to 10, to half. So we would end up with the equation that those 20 times e to the 710k are going to equal to a total of 10, half of what we initially started off with. So just like a couple questions before, we solved this exponential equation by dividing both sides by 20. And this is exactly what I was telling you, okay? Look at what we essentially did. This equation here, we ignored the initial amount, and knowing that the half-life is 710, we can just simply replace our t with 710 and equal this to half. So you could automatically skip all of this part here and start the problem right here. So from here, we'll solve the equation by taking the natural log to both sides. And on the left, this again cancels out, and we have 710k equals to the ln of half, which is in, let me just write it as a decimal, 0.5, and dividing by 710, k equals to exactly the natural log of 0.5 divided by 710. So let's see what that equals. Okay, so ln of 0.5, close parentheses, divide that by 710, equals to this number right here, which is, can it give it to me? No. It's in scientific notation, so let me just write it like that. That e here means scientific notation, which again on your calculator you should probably end up with the exact same thing. So let's say negative 9.76 times 10 to the negative 4 power. That's what that e stands for, is times 10 to the negative 4. Okay, so this is our equation. Negative 9.74 times 10 to the negative 4. And now what we have to do is evaluate this and figure out how much of this silicon 32 is going to be left after 1,000 years. So 1,000 years from when it initially had the 20. So we're going to replace t with 1,000. So let's use the calculator for this. All right. So as you see, look, pay attention to this. You can write basically this, but you can see I already have the answer there, and I'm just going to multiply it by 1,000. I forgot a 0 here. So let's clear this. And 20 e to this number, I'm just going to, this answer here, times 1,000. You can write the number negative 9.74 times 10 to the negative 4. I'm just going to simply, since it's already my answer, I'm just going to insert my answer as the exponent and multiply that answer by 1,000. And that's going to tell me that after 1,000 years, the amount of this silicon 32 that's going to be left is around 7.53 grams. So this is your answer. Now moving on to the last problem here. Now for this logistic problem, you'll simply have to evaluate. Here we have this logistic growth function models the number of people who have become ill with a particular infection, T weeks. So T represents the number of weeks after its initial outbreak. So we want to know how many people are going to be ill after 5 weeks. So that means we're evaluating this function with T for 5. So we have 23,000 in our numerator, 1 plus 574 e to the negative 1.1 times 5. So let's break out our numwork calculator out and let's type this in. Now this numwork calculator has become one of my new favorite calculators. So again, kudos to Numworks and their device here. If you're in the market of purchasing a calculator and need one for your future math classes, I highly recommend this one. So this is going to end up equaling to a total of 68, so 6,874 people, approximately that. So how many people will become ill? Well, according to this model, after 5 weeks, approximately 6,874. And there's your answer.